This is a description for project number 2 entitled Noise Removal and Classification. For various machine learning tasks, many algorithms are sensitive to outliers or noise. Even a single object can make algorithm performances quite bad. So people say a good data set is often better than a good algorithm. Here are project objectives. You will develop efficient noise removal algorithms using, for example, the KNN and the PCA and clustering with the PCA. And you will merge the noise removal algorithms to classification. And finally, you will test and tune the resulting algorithms for public domain data sets. For each of selected data sets, you will design the best model for noise removal and classification. Here, we'll start with the concept of confidence region. A confidence score indicates the likelihood that a machine learning model assigns the respective intent correctly, so that we can define a confidence region. It is the region where a new point belongs to a specific class given a confidence score or confidence value. Okay, for KNN and PCA, we'll try to define confidence region, and once the points are in the confidence region, then we'll select them, and if not, then we'll consider the points the outliers. Okay, here, so that we need a little bit of review on KNN and PCA. For the K nearest neighbors, the algorithm itself is quite straightforward and can be summarized by the following steps. Choose the number K and a distance metric. For the new sample, find the K nearest neighbors from the training data set and assign the class label by majority vote. For this data set, here there's a new point. Then from here, we'll try to find the 5 nearest neighbors. When we are choosing case 5, then it'll happen here. Then among these 5 neighboring points, now here 3 triangle points are the majority, so that in prediction, this new point will be assigned to be one of triangle points. That's the idea of the KNN. Now, for the KNN, we may define the corresponding confidence region. Okay, here select K and set a confidence value psi, which must be less than or equal to K. Then the confidence region for class, it's class by class. So for class, we try to define confidence region. Can be defined as the region where the KNN of a point includes at least psi points from the same class. So if we choose case 5 and psi 4, then now here for this example, because there are only right now 3 points here, so that is not a confidence region, so that this region is not a confidence region for the class of triangles. So in this way, we'll try to define confidence region for each class. When you are using KNN, in this way, we can define the confidence region. Now, how about the PCA? Here, maybe you need a little bit of review, but the major thing is that the PCA can be done along with singular value decomposition. And now the given data metric will be decomposed into U sigma V transpose in this way. Now, for that one, here we can define the confidence region. Now, here, let's exemplify this data set, synthetic data set. For that one, here, for each class, and like over there, for C in range of n class, for this data set, the number of classes is 3. So n class is 3. Now, XC is defined in this way. So from X, just Y as C then is collected, so that this is for each class, the data is collected. And then now we measure the class center, and now class center is subtracted from the class data, and now here with that option, so that U will become a full metric, and here we said full matrix is false. That means that this one will be now simplified only because it's two-dimensional. So 2 columns will come out for U. And now here, this is U as the sigma and V transpose. There's output. So we can get it, such a decomposition. And here, now that mu C is the cell center. And then now here we have D vectors for each class. And now sigma JC is the J's singular value for C class. Okay. Now with that notation, we can define first an anisotropic distance. Now that is for given points, so defined for a given point, and now the center is subtracted, and then here now the Vj is this multiplied with the dot product and divided by here sigma j. That is a singular value, jth singular value, and squared and summed. Okay. This function is implemented in the function iso these two in utility pca.py. I'll try to give you a packaging. In the package, it is already defined. And for some R positive, and for every R in fact, and if you consider this equation, then that equation assigns an ellipse. Okay, this is analog of this one. Okay, now in the standard coordinates, here you can make a ellipse. Now this is x-axis and there's y-axis. Now there's A and that is B. Then the ellipse can be expressed in this way. So x over A squared and plus y over B squared equal 1. So if you choose 1, then it's A. If you choose a larger value than 1, then ellipse will be expanded. If you choose less than 1, then it's shrinking. So that is exactly the analog of that equation. We are using right now standard the basis 1, 0, and 0, 1, so that for each vector over there that is projected to now this axis and that axis, then this is exactly x, that is exactly y, so that we are using x and y. However, once you are considering a general shape ellipse like that, then here this is a major axis, that is now here minus x, and then for each over there point, so that this vector must be projected here, that is exactly that projection, and divided by here now the singular value, so that the ellipse will be made. Okay. So this one will make an ellipse. Now, we define here minimum volume enclosing ellipsoid, MVEE, is the ellipsoid in general dimensional domain of smallest volume that fully contains all the points, so that for the collection of points, now we'll try to make MVEE. So the minimum volume, just enclosing every point and barely like that. So we try to find the minimum volume enclosing ellipsoid. The problem of finding MVEE not simple. However, if we consider here such ellipse, then it's really good approximation. So let's try to find the R max squared, so that from this anisotropic measure, we try to choose and put all the points, and from these values, and we try to get the maximum. That is here R max squared. Then the equation approximates the MVEE relatively well. We'll see here now. Now for the data set, and center for each class will be around here. For this one, for red points, the center will be around here. For green points, center will be around here. Now, we try to measure the anisotropic distance for each point, and then among them, we take the maximum to find this value, and along with that value, we try to make here the now ellipse. Then as you can see that here, this ellipse includes all the points from each class. And it's not exactly MVEE. However, it's around there. In fact, this ellipse may be better than a real MVEE. And the reason is that, for example, and the shape is given in this way. However, for this class, the points are more densely placed here, and then a little bit coarse over there. So if it is given, then MVEE will be made in this way, and then also the center will be here. But if you're using this formula, then center will be more or less around here with a dense area, so that even though this approximation is not accurately as the MVEE, however, that one will make here a little bit better shape, even though it becomes now larger like that. But a center will be around the density area. So that's the good aspect. But here now, negative aspect is that it is only approximation. But it's in practice, this one will be quite useful. Okay. Now, for this PCA, we may try to set a threshold, theta, or a portion and p-value between 0 and 1, so that the confidence region can be defined by one of these two things. Either the point X satisfies the anisotropic distance bounded by theta. So possibly, and theta can be chosen as here now a fraction of the maximum value. So that, for example, gamma times 0.5 or 0.6 will be okay. So in this way, you can set theta, then once it is larger than this threshold, then it will be eliminated and as noise points. And or you may use a p portion, so that from the data set only p portion of the near center points are picked from the data set ordered by the anisotropic distances. So this right figure is made along with this second choice. I said P is 0.9, so then 90% of points are picked and 10% are considered as noise. And after that, I superposed again one more LBs for each class and here, so that this here region is picked and the outside over there is considered as noise for this class. And for each class, you can do this way to eliminate the faraway points, so that after doing that, now these points are completely separated. Okay. So for this project, you must first find the confidence regions for the training data set, which can be viewed as denoising, and you may then begin the training step with the denoised data set. Okay. Then through the training, you will find the weights for each the classifiers, and the weight can be different from when you are using whole training data set. Now the data set is much clearer, and here overlapped points are eliminated in most cases. Then now the weights can be much better, so that later on, when you are trying to use, if you try to predict by using noisy test data set, and it may produce better accuracy. Okay. Okay, here, what to do? First, download PCA KNN denoising.py.tar from this site. If you click this, then you can download. Or if you try to write down this address, then it's case sensitive, so that you have to write down very carefully. And now it's automatically here make the second line, but in fact there's no space and it's connected. Okay, here the file, okay, we'll see a little bit of the file. If you download and untar, then you'll see here the files. Okay, there is these files. The KNN denoising will make a KNN denoising, yeah, and also okay, the PCA denoising. Okay, let's try to run that on Python PCA denoising. Then here you can see that one. And after finishing that, now the data is made randomly, so that each time it is making different pictures. So that let's see the figure here. That is data set randomly made. And then here, along with that, now there is MVEE. And then now after 10% eliminated, and then we can see this dark regions. This class of points are now completely separated, and that is implemented. And for so that here now for this run, this data is saved here now. Okay, let's look at that one. Okay, this data, and this is saved. Now point and label are saved, so that when you try to read the file, then last component indicates the label. So go down after 200 points. I guess it's 100 points. Okay. And then now start the class 1, and after 100 points again, now the class 2 points begin. Right? Okay. Now for KNN denoising, let's try to see that. Now for that one, here there's confidence count is defined, and then for this portion, I try to make data so that three-dimensional data along with 5 points, so that in the beginning, here there are only 2 classes right now. X0 is made along with a 5 point in 3 dimension, and also now X1 by using random number generation, and then these two are stacked row-wisely, and that is X. And for now Y, the first one is zeros, and the second one is now ones, and now they are stacked. Okay, so in this way, X and Y are made. And here for K and N, K is 5 and Xi is 4. Along with that, first here, after importing the K neighbors classifier, and we have to fit, and then now here the method K neighbors will produce the neighbor connections, and if you eliminate that one, and then also the corresponding distance are produced. And the key is this one. This method is quite useful for you. And then now here by using the confidence count and here defined on the top, and here the confidence score is made so that now confidence score is larger than or equal to the psi, the threshold, then it is chosen so that that is now denotes the x and the corresponding denotes the y is made. For each class now 5 points, and we'll run this program now, and k and n. Okay, so here xy is made 5 point for class 0, that's class number, and random generated 3-dimensional points. And now for class 1, again 5 points. For that one, the KNN is producing connections. For the 0th point, 1, 3, 2, 4 are connected, and is try to find the 5 nearest neighbor, including itself. So that there are 5 points for 0, and for point 1, now there are 5 points, and so on. So that along with that information, we try to measure the confidence score. There is 5. That means that here, for this one, and all are in class 1, so that now 5. And also for this one, all are in class 1. Now, let's look at that one here. For the 6th point, okay, now 1, 2, okay, that one is, I guess, this one, 1, 2, 3, 4, 5, 6, okay, 1, 2, 3, 4, 5, 5, 6 for that one. Now, here, there's 0.5. Now, 5, 9, 8, 6 are in class 2, class 1, but 2 is in class 1. So confidence score is counting the point in the same class, so that only 4 is coming out here. For example, the second last one, for that one, 0.8 has connection like that. 8, 9, 5 points are in class 2, but 1, 3, class 1, but 1, 3 will be in class 0, so that only the points in the same class will be now 3. So that is confidence score means. Okay. Along with that, now psi is chosen to be 4, so that that one will be considered as noise. So that except that, so that right now, for those points are chosen as the confidence point 1, 2, 3, 4, 5, and from class 0, and now there are only 4 points from class 1. That corresponding points is already eliminated. Okay, so we'll try to run one more time because it's a randomness. We'll see something that's okay. In this case, confidence scores are already larger than equal to 4, so that all are selected. So that for this generation, the data set is well separated right now, so that everything is chosen. Okay, let's do one more time. Now for that one, in this random generation, okay, here, okay, there are these 2 and that one, so that there are 3 points and here eliminated in this noise removal. That means that more points are here overlapped, and so that the data set is not well separated, so that the algorithm selects 3 points as outliers and eliminated. Okay, so try to use some portion, appropriate portions from the code, and try to finish your algorithm. Okay, here. And secondly, just compose a denoising and classification code using appropriate functions from the downloaded package. And you have to implement both denoising algorithms. One is KNN based, the other one is PCA based. And now try to use data set. You have to choose one synthetic data set and as in the project 1, and either line 7 or line 8 can be used. And then try to use iris data and wine data set. So you have 3 data sets. And now choose here 4 classifiers. And for those classifiers, just compare the performance of the algorithms with and without denoising. So already you done with part, without part, and with denoising, you have to do it and try to compare with the without denoising part. This 5 is optional for undergraduate students, but for graduate students, it is mandatory. And here, you have to add modules for clustering and PCA denoising. For example, the MVEE, the minimum volume enclosing ellipsoid, does not make sense for half-moon data set. So here, half-moon data set, if you are trying to make a half-moon data set, then data sets is around here, and another class will be around here like that. If you are choosing, for example, noise is 0.2, then the points are here spread and scattered, and also some portion are just here overlapped. Okay, and choose here now sample 400, and okay, that is now arbitrary choice. Okay, anyway, in this way you can make moon. Okay, then for the moon, so that for graduate student you have to add this data. And for this one, because the MVEE along with PCA doesn't make sense, so that you have to perform first the k-means cluster analysis for each class, so that now here for that top portion you may try to make 4 clusters for that portion, and for bottom portion again you can make 4 clusters, and for each cluster here you can do now the PCA based denoising. So for that one here, once you make some ellipse and now find the confidence region, and if the point is outside of confidence region, then you eliminate. And for each cluster, you have to do noise elimination. And then, along with the data set, you have to carry out the steps here 2 to 4. Okay? So that for graduate students, you need one more data included, and then you have to do denoising along with clustering and PCA. Okay. Now here, so the undergraduate students may consider that a class is a cluster, so that you don't need clustering. For graduate students, this step 5, the additional data and additional work will worth 40% your score. So you have to do it. Okay, this is the end of the description. Thank you.